Now, one reason why we use the LM function and not direct computation using that x transpose x thing is because the LM function is more numerically stable. That is something that you will not readily realize because you will get the same answer in such a simple case. But if your design matrix, that matrix is called the design matrix, that capital X matrix, is such that x transpose x is nearly singular, that is, this determinant is zero, is non-zero but pretty close to zero. In that case, this LM function will give you better result than using directly computing x transpose x and all that. So in our case, let's just quickly carry out that operation also. So what I will do is that I will write down that thing x transpose x, so x transpose, and I will multiply this with x, that is the multiplication sign, star hash, star and percentage star percentage x. So I created that matrix, and let me put that in some M. So let's see what M is. So M is this, x transpose x is this 2 by 2 matrix, 29, 22, 22, 26, it's symmetric of course. And let me also create N, that is, what's that? That is transpose of x matrix multiplication of y, that is N. So we want to solve M beta equal to N. So this is the system that we are trying to solve, M beta equal to N. That is not our syntax, so it's a comment. So I will write it as a comment. That hash makes it a comment. So this is what we are trying to solve, and we know that the thing that we will get is beta hat is M inverse N. So let's just see whether I can do that. The way to solve a system in R is to use the function solve M comma N. I use solve M comma N, and these are the values that I get. Let's compare it with the fit that I had earlier. So I will just quickly go to that line. LM, this is the thing that I had used. Indeed, I got basically the same thing. 2.0378 is what I got from LM, and here I get 2.0377 blah blah blah. Here I had got 0.9411, and here I had 0.941111. So in this case, I got the same answer using LM and directly by the brute force formula. So you might think that what is the use of using LM? I have already told you that this is numerically more stable. It does not use direct matrix inversion, which is a numerically unstable operation. However, there is another reason which is more important. Suppose your design matrix, the X matrix, is such that X transpose X happens to be a singular matrix. Let's just quickly create one such thing. Suppose I give you this X matrix. So I have this X matrix earlier. Where was that line that I have typed? This was the line. I have 3, 4, 2, 4, 1, 3. So what I will do is I will just do the following: 3, 4, 2, and I will make this again 3, 4, 2. So my new X matrix is 3, 4, 2, 3, 4, 2. And if you now want to compute X transpose X, let's just see that. This is my X transpose X. 29, 29, 29, 29. You have no doubt that this is a singular matrix. And let's compute my N once again. I had my last N, that is my N. And I will do the same old story again, solve M N, and I get an error because that is a singular matrix. It says system is exactly singular and some U22 equal to 0, whatever. Now let us try to apply LM in this case. So LM y tilde x minus 1. And you see, it still gives you an answer, but the answer is interesting. It says x1 is 2.752, x2 is NA. which means it has figured out that this system does not have a unique solution. However, the set of normal equations is always consistent. So if it does not have unique solution, it means it has got infinitely many solutions. So you can arbitrarily set some of the variables carefully chosen equal to 0. Now the LM function cleverly figures out that it can set the value of the second variable, that is the coefficient of x2. Remember, x is my matrix consisting of these two columns. So x2 is the second column. So the coefficient of that is what it reports under x2. So in our example it is b. It sets b equal to 0, and then of course it can solve uniquely for a. Since it has set b equal to 0 arbitrarily, so instead of reporting that as 0, it is reporting that as NA. NA means not applicable. So it says that if I set arbitrarily b equal to 0, then I can solve for A. So the presence of the NA indicates that this system is actually not non-singular. There are infinitely many solutions, and it also gives you one particular solution of this. So that is one reason why LM is preferable over the direct that X transpose X inverse thing. So we have learned two reasons why LM is preferable. One is numerical stability, which is not apparent in this example, and the other one is that it can handle non-unique solutions in a smart way. There is another reason, the third reason, which happens to be the most important reason, is that in this case we specified the entire matrix directly. Now in many cases this matrix will be huge, something like 1000 rows is not unusual, and the matrix will also be complicated. So typing out everything by hand is difficult. Then LM can actually construct the matrix from U if we specify certain structure of the matrix. And that's how we do it most of the time. And we shall see how to specify certain commonly occurring structures easily, such that the LM function will construct the design matrix internally on its own. But for the time being, that's all that I wanted to say in this video.